So this talk will be joint work with Suzy Chao, who graduated a year and a half ago, and then current work with Xin, who's a current graduate student. So the talk is about semi-definite optimization, which is a problem that has many interesting applications in learning and control. But for many of these applications, the complexity of the existing solvers is too high. So it prevents scaling to larger problems. So if you use the standard notation or the standard formulation where standard notation for SDP with an n by n matrix variable, symmetric matrix variable, and m linear equality constraints. And we look more specifically at the cost of the existing solvers. And for the interior point methods, which were developed actually 20 years ago, the solvers and even the more recent solvers are based on algorithms that were developed 20 years ago. They don't scale well because per iteration the computations will, for a dense problem, include terms m cubed, where m is the number of equality constraints, because you have to solve at each iteration a fairly dense m by m set of linear equations. And then other terms for actually constructing that set of linear equations include terms m squared, n squared, mn cubed. So if m and the matrix dimension n are of the same order, it's n to the fourth. And if in the worst case m could be order n squared, then it could be n to the sixth, which is very high. And in some applications, it's possible to customize interior point methods to exploit structure, but it's not easy. Then, as an alternative, maybe the first thing that comes to mind today are the methods like ADMM and all the proximal splitting methods, which have been used in many large-scale applications in learning and other applications. So in those methods, it's very straightforward to exploit linear structure in the equations, because you just have to multiply with the coefficient matrices or solve linear equations defined by the linear constraints. But you still have the problem that in the standard proximal methods, at each iteration you have to project on the positive semi-definite cone. And that requires an eigenvalue decomposition. X in general is a dense matrix, so that would add a term n cubed to the complexity. So that's also quite high. So in this talk, we'll look at actually two types of structure in specifically. So the first one is sparsity. So a sparse SDP would be one where all the coefficients AI and C, are all very sparse with very a lot of overlap between the sparsity, between the zeros in the constraints. So that's common in learning applications that involve graph optimization problems, for example, SDP relaxations of different types of clustering or partitioning. But then, of course, you want to scale it to large graphs. And another application was mentioned this morning is in polynomial optimization, where you look at sum of squares relaxations of polynomial optimization problems. And they're often the polynomials themselves are very sparse, the coefficients of the monomials, and that's very important because the problems get quite large also quickly. So if you look at maybe the simplest and the oldest, one of the oldest examples of this type is the max cut problem. So you're maximizing a linear objective. L in the objective has the sparsity of the graph in the max cut problem. And then linear in this case, m is n, so we have just these linear constraints. So in this case, m is n, so a standard general purpose interior point solver would have a complexity n to the fourth. It's also an example where it's actually very easy to customize an interior point solver and reduce n to the fourth to n cubed by a very simple modification. And in this case, if you apply ADMM or a proximal method, because of the projection on the positive semi-definite cone, you also have n cubed, which is actually not better than this customized interior point solver, and actually will take many more iterations and be less accurate. Right? Of course, for a more complicated problem, the n cubed would be not possible. You would have n to the fourth or maybe higher, but it shows, in any case, n cubed might be too large for practical applications. And a similar observation can be made in many control applications. So many of the applications of semi-definite programming in control and system theory in the 1990s and 2000s were related to theorems, sum of squares theorems about non-negative polynomials and trigonometric polynomials. So maybe the simplest example of that is a non-negative trigonometric polynomial. So sum of complex exponentials with coefficients xk. So this is non-negative. So the constraint on x that this is non-negative is a convex constraint on those coefficients. And that cone of non-negative polynomials has a semi-definite representation because it can be represented exactly by a sum of squares that we'll discuss in the first part of the talk. But it's easier to actually say in words what it means for the dual cone, because the dual cone of the cone of non-negative trigonometric polynomials is a cone of positive semi-definite Toeplitz matrices. So the primal and the dual cone are SDP representable exactly. So that's the simplest example of an exact sum of squares theorem. Many applications in control involve extensions of this to rational functions, to matrix polynomials, and so on, right? And more recently, also this fact has been used in papers on gridless compressed sensing or a compressed sensing type application where you don't discretize the frequency axis. And we'll see an example of that later. So here also, if you look at the complexity of solving a problem that involves this constraint of this form, assuming that this is the most difficult constraint in the problem and the rest, the objective function and the other constraints are straightforward, but this limits the complexity. Then for a general purpose solver, you'll get into the fourth per iteration, a general purpose interior point solver. Again, it's easy to customize and bring that down to n cubed, which would also be the complexity of an proximal method, because if, for example, if you look at the dual problem, you have to deal with a cone of positive semi-definite Toeplitz matrices, then it's not possible to or efficiently project in the Euclidean norm on that cone. So you have to split it in the projections on Toeplitz matrices, which are easy, and projections on the positive semi-definite cone, which involve an eigenvalue decomposition. So here also you would like, in any case, to scale it to so if you look at proximal methods, so a very nice classical idea in the theory of proximal methods is to look at, improve the complexity by replacing the standard proximal operation by proximal operators that are defined with a generalized distance or a Bregman distance. So that's sort of the purpose of the talk. So to look at, we look at these two types of applications, sparse SDP and then trigonometric non-negative polynomials, and then try to reduce this n cubed or higher complexity by using an proximal or defining proximal methods that involve generalized distances. So I'll start with some background on proximal or Bregman distances. So proximal methods get their name from the proximal mapping, which is defined like this. It's the proximal mapping of a function f maps a vector y to the solution of this regularized optimization problem with this, the Euclidean norm as regularization term. So it maps y to the solution x of this problem. And so this was introduced by Moreau in the 60s, and he showed that if f is closed and convex, then this has a unique solution for every y. Even if f has could be non-differentiable or have a domain, this always has a unique solution for every y. And then there are many types of proximal methods where that use this operation. So maybe the most fundamental one is a proximal point method. That's just a fixed point iteration, fixed point algorithm that repeats this proximal operation. If you apply it to the dual, you get augmented Lagrangian method or the method of multipliers. The proximal gradient methods minimize and use this to minimize a function, a sum of function f and a differentiable convex function. And this is the iteration, so you take a gradient step for the differentiable part in the objective and then apply the prox operator for f. ADMM and several methods related to the Douglas-Ratchford splitting method use this. And then maybe the most recent one in the list are the primal-dual hybrid gradient method, or the Jumbo-Pock method is a primal-dual proximal method. So if you replace this with the generalized distance, the idea is to replace the squared quadratic distance with the generalized distance, dx of y. So for example, in the proximal gradient methods, if you, if this is the proximal gradient step, and you plug in the definition for the operator, you get this more explicit form. So at each iteration, we keep the non-differentiable part of f of the objective. We linearize the differentiable part and add this quadratic regularization term. And xk is the previous iterate, and the solution of this problem is the next iterate. So in a proximal gradient method based on the Bregman distance, you replace the squared Euclidean distance with a Bregman, or generalized distance, and define this as your proximal gradient method. This is sometimes referred to as preconditioning, and then preconditioning would mean that you do this in order to obtain a method that hopefully converges in less iterations. Another goal could be to just make these proximal operations, these subproblems, easier to solve. And that's actually the purpose in this talk. We want to really expect the number of iterations to be smaller than in a standard proximal method, but we're hoping to use a distance that makes this easier to compute. So d here is a generalized distance. So Bregman distance is defined like this. So you take a kernel function phi, a convex function phi, generates a Bregman distance, and the Bregman distance generated by a kernel function phi is the difference between the value at a point x and then the linear approximation at y. So you get this definition, that's the definition of a Bregman distance, generated by a convex kernel function phi. So phi has to be convex, differentiable, because you need the gradient. And in practice, depending on the algorithms and the type of convergence result you're interested in, you may have, of course, to impose other conditions, like strict convexity or even strong convexity. But the most important ones are certainly differentiability and convexity for the definition. Right? And in general, the kernel function will have a domain that's not all of sort of a restricted domain, because we use the Bregman distance to implicitly represent some constraints in the problem. So if you look at the definition and you see that this generalized distance x between x and y is defined for all x that are in the domain of phi, because you need phi of x, and for all y that are for which the gradient is defined, which would be the interior of the domain. So that'll be important later. So it's not really a distance because it sort of lacks some of the properties of a real distance. For example, it's not symmetric. If you flip x and y, you get a different number. And, but that's okay, because if you look at how we use this, for example, in a proximal gradient method, the second argument of the distance that we use here is xk. So that's the previous iterate of a variable xk. The next value, x, the first argument, is the next value, xk plus 1. And we run the algorithm in one direction. We can always compare xk to the next xk plus 1. So it's now clear that actually symmetry is important, because you would never run the algorithm in the other direction. Right? And of course, another important difference with the standard distance is that this is not defined for all x and y, because in applications, phi has a domain. Right? So then we can use this as in the definition of a generalized proximal operator. There's one small thing to mention in the definition. So if you use, this is how we'll define a generalized proximal mapping with the distance function d. So we have a function f, and this defines a proximal mapping of a function f. We have a general linear term for an arbitrary a, and then the distance from between x and y. So the standard proximal mapping is a special case where you use a squared Euclidean distance for your distance. And if you use that as your choice for d, then you can make a simplification, because you can move the linear term inside the norm. And you get something that only depends on the difference of y and a. And you get, this is the standard definition of the proximal operator of f, evaluated at y minus a. In the general case, you cannot do that. You cannot move the linear term inside the norm for a general distance, so you have to really keep it in this form. Right? So we'll always, if we need a notation, we can use this, but it's easier to actually make it explicit and write out the minimization problem. So for the standard proximal operator, we know f constant is well important question, because when we use a certain distance, it's because we know an efficient way of computing the solution of this problem. So actually, we know just from the existence or the availability of that fast method, we actually know there is a unique solution, and it's uniquely defined for every choice of A, right? In the applications where we're trying to use this. So that's the most important criterion will be that this is inexpensive. It has to be inexpensive for any possible choice of A and any possible choice of Y in the interior of the domain of the kernel. And it's also important that the result of this minimization is actually in the interior of the domain of the kernel, because the result of this minimization will be used as your Y in the next iterate. Right? So the standard or the most best known application of this is the entropy. So if you take the Bregman distance for the negative entropy on the non-negative orthant, then you get the relative entropy as a generalized distance. And it's interesting because if you do the generalized projection on the hyperplane, then there is a simple closed form formula for this generalized projection. So if you just take, in this case, it's a generalized projection or the proximal operator for the indicator function of this hyperplane, you can actually solve this analytically, and that's the solution. Yes? So the intuition depends on the different methods, but in the proximal gradient method, this would be the A vector, would be the gradients. So this is actually how the proximal operator appears. So f of x, then xk would be constant. This is the A vector, and this is sort of this proximal operator definition. Right? And then in other applications, it could be something else. Right? So that's a picture. So these are the contour lines in the, so that's a probability simplex in R3. That's the contour lines of the negative entropy. This is the relative entropy centered at Y. The relative entropy centered at Y. So if you take a general A and look at this subproblem, then you get a solution that you can easily compute, and it's somewhere in the interior of the probability simplex. Right? And that works because the entropy has this property that it's finite everywhere on the probability simplex, but the gradient increases to infinity as you approach the boundary. Right? So as a result of that property, the solution of this projection problem will always be strictly positive. So this is used in the, if you use this in a proximal point method, you get the entropic, it's called the entropic proximal point method. And the dual application of that is known as the exponential method of multipliers from the 70s. So in the next two parts of the talk, we'll apply that to the two applications. First, the non-negative trigonometric polynomials, and then sparse SDP. So the first constraint that can be represented by semi-definite programming constraints, as I mentioned, is this. So we have a cosine polynomial and a trigonometric polynomial. But for simplicity, I'll take the coefficients to be real. So it's a cosine polynomial. If you take them to be complex, you also include sines. But for simplicity, we'll take the real variables. And the constraint is we define a cone K of coefficients of these cosine polynomials for which the polynomial is non-negative everywhere. That's a convex cone K. We'll normalize it by normalizing the first component to be 1, sort of the counterpart of the sum of the xi's is 1 in the entropy case. But that's not too important. Other types of normalization might work. You might have an upper bound on x0 would also work. So this, as I mentioned in the introduction, has a semi-definite representation and is actually explained here. So we define a linear mapping D that maps a symmetric matrix of size n plus 1 times n plus 1 to a vector of size n plus 1, and it just computes the diagonal sums of the matrix. So the first element of D of x is the trace of the matrix. The second element is the sum of the elements on the first subdiagonal, then the second diagonal, and so on. And the last element is just the last element in the first column of x. Right? So that's the linear mapping that maps this n plus 1 dimensional symmetric matrix to a vector of length n plus 1. And the SDP representation of this cone is that x, the polynomial defined by x, is positive, is non-negative everywhere. If there exists a positive semi-definite matrix X that's mapped on X under this linear mapping, right? So we would like to handle this cone using or find a suitable Bregman distance for this cone. And sort of there are different, maybe the first candidates, if by analogy with the relative entropy, would be to use this as the kernel function. So you take the cosine polynomial and then take this convex function of x as a kernel for a generalized distance. And that would give you the Kullback-Leibler distance. These are the contour lines of this kernel function for a three-dimensional cone. So it's a three-dimensional cone, but we normalize the first component to be 1. So this is a section of a three-dimensional cone, right? So it's a nice convex function. It's defined everywhere, including the boundary. It's actually, there are efficient methods for projecting using the generalized distance and the Kullback-Leibler distance. And that's even explained in standard textbooks on speech processing, how to do this using FFTs. But in our methods, there would be a problem because you can see from the contour lines that the function is finite on the boundary, but the derivative doesn't go to infinity. So if you use this in a generalized distance, you wouldn't have the property that we saw in the relative entropy case, that the result of the projection is always in the interior of the cone. And that's important, at least for the algorithms that we'll discuss. So an alternative is to use this convex function, which is also convex in x. And that defines what's known as the Itakura-Saito distance. And it does have this property. So these are the contour lines of this function phi. It's again convex, defined everywhere, including the boundary. And but now we see the gradient goes to infinity near the boundary. So the result of a projection will always be strictly positive with this distance. So the term that Rockefeller uses for this property is that this function is essentially smooth and the first one is not. Right? So we'll use this as a kernel for the Bregman distance. So the questions to consider are how to evaluate this efficiently, its gradient, and then how to do the projection on this with this Itakura-Saito distance. So this function has actually very nice connections with system theory and control. So first, if you want to evaluate this kernel function, this entropy-like function for a given x, then we can actually evaluate this by solving an SDP. So in this problem, we fix x, the coefficients of the cosine polynomial. We have our SDP representation in terms of a matrix X, and we maximize just 1, 1, the first element of the matrix. But here we start the indexing at 0, so it's the x0, 0 matrix element of this matrix X. So the matrix X that's positive semi-definite is mapped to the vector of coefficients under this linear mapping and has a highest 1, 1 element. Gives you the value of this function. If you take the negative of the log of that optimal value, you get this phi. So that's why we write it not just as, of course, here what we're doing is we maximize x0, 0, but if you take the negative log, you get this function at the optimum. Also, it's known that the optimal x has rank 1. So the optimal x of this problem will have rank 1. So you can write it as BB transpose. And so it also means that x, the optimal x, actually solves this quadratic set of equations. For given x, D is a linear mapping. So D of BB transpose is a quadratic in B. And the solutions B of this quadratic set of equations are called spectral factors of F. And by maximizing the 1, 1 element here, we find the minimum phase spectral factor. So the B that defines a polynomial that has no zeros outside the unit circle. And actually so you could compute this by solving an SDP, but actually a very efficient method for computing X is actually just to apply Newton's method to this quadratic set of equations. That's a very classical method for spectral factorization, and it can be shown that it always converges, and it converges quadratically. And the Newton equations that you have to solve have some interesting structures, so you can do this efficiently. So that gives us a way of evaluating the function. We compute the spectral factors of x, the minimum phase spectral factor, and then you get the function value of phi. Right? So the next question is the gradient. So in this problem, we fix x, the right-hand side of this in this SDP. So from convex duality, we know that the gradient of the optimal value will be related to the multiplier in the dual problem, the optimal solution of the dual problem. So the dual problem of this convex problem can be written after some simplifications like this. So you maximize a function of y, and y is the multiplier, Lagrange multiplier for these equality constraints. And this function psi is defined like this. So T of y is the Toeplitz matrix constructed from y. The domain of this function are the vectors y where that Toeplitz matrix is positive definite. Then this E transpose T inverse E is the 1, 1 element of the inverse of the Toeplitz matrix. So E is just the first unit vector. So we take the first element of the inverse of that positive definite Toeplitz matrix, and then take the log, and that turns out to be a convex function of y, and it's up to changes in sign. It's actually the conjugate of this entropy function, or the convex conjugate, or Legendre transform. So it's a convex function of y. And then by duality, strong duality, the optimal value of this problem is also the kernel function, because this is the dual of this first problem. And the optimal y gives us the gradient of the function. And the gradient can also show that the optimal y can be computed from the solution of the primal problem, the spectral factor, because it's the Toeplitz matrix that satisfies this equation. So usually in signal processing, these equations are very common. So T is a Toeplitz matrix, B is the a vector, E is the first unit vector. So if y is given and you solve for B, then that's called the Euler-Walker equation. Here, actually, we fix B and we solve for y. So it's bilinear in y and b, so if you fix b, you can solve for y. And that can be solved by algorithms that are very similar to algorithms for the Euler-Walker equation. And it's actually a reverse form of the Levinson algorithm that solves this. Given b, compute y. So that can also be done quite efficiently. Yes?
So this is a convolution? Is it like a convolution?
The equation?
Yeah.
More like a correlation. So usually in y would be a covariance matrix, and then you solve for b in like linear estimation, the Levinson filter, and E is just 1, 0, 0, 0. But here you're given b and you solve for y, but the whole thing is still linear in y as well. Right. So the standard method for solving this equation for b is the Levinson algorithm, or that's like the first fast algorithm for solving this. And then it turns out that if you reverse Levinson's algorithm, you get something for solving for y given b.
I see. But so systems theory interpretation is that this b is the filter. So you started from a transfer function?
So you start from x, that's positive, f of x is positive, the coefficients of a positive trigonometric polynomial. The first step is to do the spectral factorization of f, and the minimum phase spectral factor is this vector b.
So easy.
That's easy to compute by spectral factorization. Then that gives us the value of this kernel function. Then by solving this for y, you get the gradient of the kernel function at x. Because that's the y here is the solution of this dual problem. And that's also easy. Right? And then the most important question is, of course, to do the projection with this distance defined by this. So this is a Itakura-Saito distance. If you take the distance defined by this kernel, you get something that looks like this. It comes from speech processing. It was actually studied in the 70s as a way of comparing power spectra in speech. So if you use this as distance, this is the optimization problem we have to solve. We have, again, an arbitrary vector A, our distance dxy, and then we normalize the cone of positive definite polynomials by this normalization constant. So if you use the definition of D and move the linear term, combine the linear terms, you get a problem like this that you have to solve for the projection. So it's an unconstrained or a convex problem with one equality constraint. So the dual problem will have just a scalar dual variable for this constraint. It looks like this. And so one way to do this generalized projection is to solve the dual problem or to solve the KKT conditions for these two problems. So if you solve the dual problem, then it means that at each iteration you have to solve for a given, if you want to do the projection for a given A, you solve a convex problem or a convex minimization problem over a single variable lambda. And to solve this, you can use Newton's method. And at each iteration, you have to compute the gradient and the derivative and the second derivative of this function h. And that can all be done from factorization of a positive definite Toeplitz matrix. So at each iteration, you have this Toeplitz matrix T of C. You add a multiple of the identity that makes the resulting Toeplitz matrix positive definite. And then you have to solve for this vector, so the inverse times E. So that can be done in order n squared operations using the Levinson algorithm. And there are actually many faster versions that people refer to as super fast Cholesky solvers that do it in less than n squared, and the complexity, I think, is n times the square of log n. That's maybe the fastest ones. So if you accept the fact that Newton's method for solving this one-dimensional problem will take a number of iterations that's fairly small and not too dependent on the size of the problem, then the cost is really dominated by the cost of solving these positive definite systems, which is n squared or maybe better. So you have a generalized proximal operator with a complexity of order n squared, as opposed to n cubed with the standard proximal. So this is an example from this gridless compressed sensing literature. So here the purpose would be to fit a signal, parameters in a signal model like this to data. So we have a sum of complex exponentials plus white noise. And almost everything here is unknown. So the noise level is unknown, the number of terms, rho, the coefficients, the position of the frequencies, everything is really unknown. And under some classical assumptions in statistical signal processing, so of course the white noise is random, and also you assume that the phases of the coefficients are random and uniformly distributed. Then the covariance matrix of a sequence of values of V of t has this form. It'll be a Toeplitz matrix with low rank, rho, or rank 2 times rho. So low rank Toeplitz matrix plus a multiple of the identity. And the multiple of the identity is the noise variance. So in this problem then, we try to fit a covariance matrix of this form, so a Toeplitz matrix plus a multiple of the identity to some sample covariance matrix. we're adding the trace of the Toeplitz matrix to make it low rank. And then we add a constraint that must be positive semi-definite. Right, so that's so this would be an example where we have the reconstruct the exact positions almost of the frequencies omega k. The solid line here, so we solve not this problem, but we solve the dual of this problem, which is a problem that involves the dual constraint and these non-negative trigonometric polynomial constraints. So the solid line would actually be the solution of the dual problem, a non-negative polynomial, and where it becomes zero by complementary slackness, that's where we have the pulses or the lines in the spectrum of this model. So the method we used this generalized proximal operator to solve the dual problem, and the method is called the IGA method, and this is sort of the gap or the accuracy versus iteration. And the IGA method is actually, that's the improved gradient algorithm, was proposed by Auslander and Toeplitz, and it's the Bregman extension of one of Nesterov's fast accelerated proximal gradient methods. So this is one of Nesterov's, if you're familiar with the accelerated proximal gradient methods, this is exactly the same, but the second step replaces the standard proximal projection by a generalized projection. And it converges, so the convergence conditions are very similar. So if f is convex with the Lipschitz continuous gradient, then you can show a 1 over k squared convergence for this accelerated method. So we tested this on sort of a family of problems that are simpler. So here we project a given A on this set using this formulation. So the red line would be a standard interior point method called via CVX. So here, as expected, we get n to the 4th complexity. And with this fast Itakura-Seidel distance, we get something that's very close to n squared. But the n squared, because the cost of one projection is roughly n squared. So that's the first part of the talk. How much?
We would have 10 more minutes.
Okay, so the second part is shorter. So in the second part, we try to do something similar for the sparse SDP case. So a sparse SDP would be a problem where all the coefficients are very sparse with many common zeros. We can always assume that the sparsity pattern is choral or a filled Cholesky pattern. And then a difficulty in SDP is, of course, that to be feasible, X would be, in this problem, would be in general be dense, to be positive semi-definite. But one useful observation that people have made in algorithms for sparse SDP is that you can really look at the variables in X. There are two kinds of variables in X. There are the elements that are multiplied with non-zeros in the cost function and the constraints. And those are really the optimization variables. And the other variables must have values that make the matrix positive semi-definite. So you can look at this problem also equivalently like this. You, instead of optimizing over a full matrix X, you optimize over sparse matrices X. The cone is not a cone of positive semi-definite matrices, but a cone of matrices that have a positive semi-definite completion. So to some extent, it's just notational, but sort of mentally, there is a big difference between the two problems. Here, it looks extremely large scale because you have an n by n dense matrix of variables. Here, you have a sparse matrix of variables. So this looks much more doable than the original problem. And if you really look at distinguish these two types of variables, right? So E here will be the sparsity pattern. S and E is a set of matrices with sparsity pattern E. And then the cone here is a cone of positive semi-definite matrices, completable matrices. So again, we would like to find suitable Bregman kernels for Bregman distances. So the matrix entropy exists, but unfortunately requires eigenvalue decompositions. So that's wouldn't be useful here. So instead, we'll use the logarithmic barrier function for this cone of completable matrices. So the cone of the logarithmic barrier function will be defined like this. It's easier to give a barrier function for the dual cone. So the dual of the cone of completable matrices is the cone of sparse positive semidefinite matrices. So there we can just use the standard log-det barrier function. And then from the convex conic optimization theory, we know that if this is the barrier function for the dual cone, then a logarithmic barrier function for the primal cone is defined like this. So the maximization of this over all S in the interior of the dual cone. And then if this is the barrier function, then we can, so instead of, because we use the barrier function, this as a kernel for the Bregman distance, we cannot really apply it to the actual SDP directly, but we can solve the centering problem of the SDP, where you actually add a small multiple of the barrier function and remove the inequality constraints and get this optimization problem. So this is, gives you suboptimal solutions for the original problem. But if you look at distance defined by this kernel, so that's our logarithmic barrier function. The S that solves this maximization problem in the definition is, in general, the inverse of the maximum determined positive definite completion of X. So if you evaluate the barrier at a positive definite completable X, then the S that solves this convex optimization problem is the inverse of the maximum determined positive definite completion. And it's, the inverse is in general sparse, where the maximum determined completion, of course, would be dense. It also gives you the gradient. If you look at this definition, the same S gives you the gradient of this function with respect to X. And for choral sparsity patterns, so the first things are actually always true, but for choral sparsity patterns, there exist very efficient methods for computing this inverse of the positive definite completion. And you get algorithms that have a very similar complexity as just a sparse Cholesky factorization of a sparse positive definite matrix with that pattern. So suppose we use the Bregman distance defined by the logarithmic barrier function, apply it to the centering objective function, so just the objective function of the centering problem, with some kind of normalization constraint on the trace of X. Could be an equality, or trace of X is less than some upper bound, or maybe some, you could also replace the identity with something different. But suppose you have some normalization condition that bounds the feasible set. Then this would be the problem that we need to solve to compute the generalized projection for this centering objective. And again, if we solve that via the dual problem, by introducing a multiplier for the normalization constraint, then you get a convex problem with a scalar variable. And it looks just like this. It's the log-det of some matrix B, sparse matrix B, plus a multiple of the identity minus lambda. So it's a simple convex optimization problem with one variable lambda. And we can solve it by Newton's method. So we can solve this primal problem, or the dual, or the optimality conditions, which would be this. So at each step, we solve this nonlinear equation and a scalar variable lambda. The equation is that the trace of the inverse of this sparse positive matrix B plus lambda I is equal to 1. And you want the largest root of that equation. So if you solve this by Newton's method, for example, then you have to evaluate this function for each lambda at each iteration, its derivative, which is defined like this. And then from the optimal lambda, you get the optimal solution of our generalized projection, which would be the projection of the inverse of B plus lambda I on the sparsity pattern. So each of these operations, so evaluating this trace of the inverse, trace of the squared inverse, and then the projection of the inverse on the sparsity pattern, are all very tractable. Because these are questions that actually have appeared and have been discovered and rediscovered multiple times in linear algebra. So here we have a sparse positive definite matrix B plus lambda I. The inverse in general will be a dense matrix, but we need only the trace of the inverse. Or here we need only the elements of the inverse in the positions of the non-zeros in the sparsity pattern. And that can be, so we don't need the complete inverse to compute these quantities. We need only the elements on the diagonal or on the non-zeros in the matrix B, and that can be done very efficiently from the Cholesky factor of B plus lambda I. The complexity that's also comparable with the cost of a sparse Cholesky. So again, the conclusion would be that if you solve these generalized proximal operators by Newton's method, apply to a simple nonlinear equation, then and you accept that the number of Newton iterations is small and fairly independent of problem size, then the complexity would be the cost of roughly a sparse Cholesky factorization with the sparsity pattern E of the problem. Right? So if you can do this sparse Cholesky factorization, you should be able to do these proximal operators. So we tested this on some examples. The first is a max cut problem. So we solved this centering problem, and these are graphs of dimension up to several 10,000. We use the Chambol-Poc method that I'll discuss in a minute. So the number of iterations is what we would expect in these types of methods. It's several hundred. And then actually, I removed the wrong column. This should be the number of, this is not time per Cholesky factor, it's the number of Newton steps per proxy evaluation. So it's fairly small. This is a more complicated problem. That's a graph partitioning relaxation, where you partition a graph in two equal sets. So it's more dense because P here is a sparse basis for the complement of the once vector. But again, we can solve fairly large problems. So the method we use here is a primal-dual hybrid gradient method, or the Chambol-Poc method, or at least its extension to Bregman distances. So it solves a problem of this form. You just have a general convex function f with equality constraints. And at each iteration, we have 3 steps, and the second one is sort of a generalized proximal operator. And the other, the matrix A here, just is involved in matrix vector products with X, and then the transpose or the adjoint of A is multiplied with Y. So that's the, maybe to summarize. So we looked at 2 examples of SDP representable constraints with some interesting structure. Non-negative trigonometric polynomials and sparse SDP, and try to formulate proximal operators in terms of a generalized distance that can be evaluated at a cost that's less than n cubed. The first one was it is Itakura-Saito distance. The cost is really dominated by an Toeplitz Cholesky factorization, so roughly order n squared. And the second example, we applied this to the centering problem, not the original SDP, but the cost is dominated by the cost of a sparse Cholesky factorization with the same sparsity pattern E as in the problem. Right? So that's much less than n cubed. Thank you.